This is lecture 9 of CS47 computer organization study. We'll be continuing with the memory usage, and as we last lecture 8, we started with the understanding of how we can write and read to and from into the memory, and also what is the general convention in the software world to actually access or use different part of the memory, different address spaces of the memory for specific purpose. We also mentioned that this is purely software convention, and as a hardware system does not prevent that. All this restriction is imposed from either operating system or compiler, or to some extent at the assembler level. But at hardware level, no one is going to restrict to read and write into any address of the memory. Okay, the segmentation of the memory, dividing that into different address spaces for different purpose of usage, is purely a software convention. We have couple of topics for this lecture, so we'll continue the memory model from the last lecture, and then we'll talk about stack operations. So this is again not the data structure stack we are talking of. The operations have the same notion, but will be, this is what the dynamic memory area, and correspond to that we'll discuss about the stack convention. Again, this is another software convention, nothing from the hardware. Software convention of the stack memory, dynamic memory usage. We'll talk about these, and then last part, but definitely not the least, is discuss about global and local variables in terms of assembly. This is a little different notion than what we understand as global and local variables in the high level language. All right, so we'll try to understand local and global variable at low level, okay, at the assembly level. So we continue with the memory model, and let's say we load this memory. Like, this is a very similar experiment that we did in the last lecture. Especially this data layout is like a byte and characters, a half word, like word, etc. So we introduce another, like where C level, which is another byte, and we need to observe how these variables are placed in the memory and their addresses, right? So we want to do it through the experiment, and then these 4 instruction, load byte, half word, and note that these are pseudo instruction since MIPS support only register relative addressing. So in previous lecture, we also observed in one of the experiment that we can do load byte, half word, etc., and refer to a label in the data section, or any label as such. So it basically tells that I want to operate some memory instruction like read or write at this address, which is assigned for this label. Like, for example, LH $S1, var B. It notion is that we want to load a half word starting from address, which is assigned for label var underscore B in the symbol table, and that to half word value should be loaded in S1 register, and this is a signed load. It is not LHU, it is LH, means signed half word should be loaded into S1. So these two things we'll observe in this experiment. So before we experiment, before we explain this slide, let's go to the experiment and do our experiment. So I'll load that program experiment 11 in the Mars. Okay, I have made that here. Okay, I need to change this guy, right? And then so yeah, then assemble it. So as I see, your variable A address is starting from 1001.0000. That's a dot data base address for Mars IDE environment, and it places a 10. Then my next layout was a half word 3210, which is starting from 1001.0002, which is like this is a 0, this 2 byte is 1. Yeah, this one 3210, like the last experiment we did. So it's starting from there. So in the last experiment we also talked about this little mysterious gap, why the var b is not starting from 1001.0001 but from 02, and we said that we'll explain in this lecture. That's what we're trying to do here. And then the var c is going to be at 1001.0004 address var c, and then var d certainly appearing at 1001.0008, right? All the upper 3 bytes remain 0, and suddenly that word value shifted further towards this address, right? So that is observation 1, and observation 2 is that all these load memory load instruction at line 22, 23, 24, 25 are practically pseudo instruction on the basic. They become something else using 80. Okay. Now let's get back to our slide and try to explain this phenomena. So my variable A, that label, it starts from the start address. Okay, the B went here, C went 004, and D is starting from 008, leaving a 3 byte gap, right? This is what problem? This is the problem of data alignment. Okay, this phenomena is called a data alignment. If you ever heard a term data alignment in context of high level program, at the low level this is what it's meant. It means that not every type of data, like in terms of like in assembly it is basically byte, half word or word, unlike high level has more variation of different basic data like integer, char, boolean, this and that. At basic level they becomes like either byte, half word or full word. Not all of them can start from randomly at any address. There are certain rules. The rule is this: your byte can start at any address value. Okay, your half word can only start at an address which is even, like divisible by 2, and a word can start from an address which is divisible by 4. So what is happening here, following that rule, my first variable A, which is like that label A, which is like, let's call it a variable just in a very loose term, but their label, like variable A is starting from, this is a byte, so I can start from any address, and when assembler start laying down this data into the memory, start from this address 1001.000. So it put 10 into that byte position. So my next available address is 1001.0001, right? This next address. Now at this point, I'm requesting assembler to make a half word. But half word, remember by rule, it cannot be placed starting from an address which is odd value. So we must move to the next available even address, which is 1001.0002, and it will span 2 bytes. So this is a little endian convention, 3210. Then next VAD-C, I'm requesting as a byte, and next available address after placing my half word is 0004. I'm not repeating that 1001, okay, it's there. So 0004 is my next available address, and byte can be placed anywhere, so it will just go and be placed on that 004 address. And my next free available become 0005. At this point, I'm requesting assembler to lay down a full word. A full word by rule, it has to be started from an address which is divisible by 4. So next address, like after 0004, next available address which is divisible by 4 is your 0008. So VAD-D is placed at that point, starting at that 0008. And that is explanation of those mysterious gap that is coming out after I lay out my data from an assembly program. Okay, these are wastage of space, no doubt, but this is the rule it has to follow. Now, same code, let's do this thing. Let's make an addition of the line dot align 0, and we'll see what happens. This alignment dot align, please look at your textbook appendix, last appendix, where it actually go and talk about all the different directives and instruction, etc. Dot align 0 force the Mars to put following data into continuous location. So it's telling assembler that don't follow the alignment rules for any type of the words, right? It's you don't need to follow half word to start from a even address. You don't need to follow word has to actually start from an address divisible by 4. Just continuously place those data, right? Just don't waste spaces in between. So with that, we'll see that your var A going into first address, var B will be placed into the next address, like starting from 1. It's not following the rule since I put a align of 0, alignment 0, and the next byte is at this, and word is at 4. So among this placement, if you look at, first of all, there is no space wastage, that's fine, and the word has been placed from an address which is divisible by 4, which is also good. Problem only is the half word has been placed at an odd address, so which is not allowed. And what will happen if I run this program? Okay, whenever I am trying to make a load half word from the variable B, system will complain. Let's see that. Okay, let's put the Mars again dot align 0. By the way, before that, even like if I assemble this, run this, no problem, right? It can run. Now I put align 0, save, assemble. So now see, as predicted, variable A, B, C, D are placed such a way, are assigned those addresses in such a way there is no waste of space, right? See that everything is compacted now. 10 is placed, then 3210 is placed, then 20 is placed, then 76543210 is placed. No gap between them. I run it. Now see, error in this line, runtime exception, fetch address not aligned on half word boundary 1001 0001. So system crashed, system got an exception. Okay, so that's what happens if you don't follow an alignment upon accessing the memory. Your assembler will be fine, it doesn't complain, but at the runtime it will cause an exception. Okay, cause an exception, and it will just come out with error with some messages. So what to do? We have achieved the compactness of the memory, but we haven't. This program is now unusable, right? So next part, what we'll see now is to little bit make a difference between in my code, right? Whatever we write, what we want to do, swap the variable b and c position. Then what will happen? Your first is byte, second is a byte, right? 20. Then third is a half word, which is now starting from your even boundary, right? So 10 is placed, 20 is placed, 3210 is placed, and then your word, complete word is placed. And with that, this load half word on the variable b level now won't have a problem. Load half word on the variable b, yeah, level won't have a problem, because that's half word is now starting from a even location, right? So just tweaking this sequence, we can save our day, right? So let's look at that in here. So instead of doing this, yeah, I think this one I wanted to do there. So I don't want alignment. I have, let's do that, and C comes first, then B, then this. Now assemble. Let's clear this and this, and we see our compactness, no wastage of space. Run it, no problem, right? The exception doesn't come because we are all are accessing memory in order of its alignment. Okay, in a right alignment, aligned address. What I should say is a right alignment address. We are accessing these memory locations. We are accessing bytes, doesn't matter, any address. We are accessing half word from even address. We are accessing words from an address which is divisible by 4. That's what system wants to confirm. Okay. All right. So now data alignment in the memory, even in the high level program, it is important. Why? Let's say this byte half word, byte half word. Let's say I have a record structure which uses character, short character, integer, right? This is the same sequence as a byte, character for byte, short is half word, another character byte, this is word. So if that structure compiler compile it like this sequence, like the experiment we started with, then we have lot of wastage spaces. It doesn't seems like this is like 4 byte of wastage space, which is a word. It doesn't seems like much at the beginning, but assume you are actually handling and storing like millions of such record with this structure in memory. For 1 million, you are actually wasting 4 megabyte of space, right? At the high level, you can reorder this like char short int, and that actually you will save that 4 megabyte wastage, assuming you are using 1 million such record. Okay. Now compiler nowadays are intelligent. They actually look at these alignment issues, and when it kind of try to lay down at the assembly level this variable sequence, it basically go through the alignment requirement and can reorder the variable automatically in most of the cases. But for complex data structure, like you are having like too many references and too many pointers to pointers and those kind of things, it's sometimes they fail. Okay, sometimes they fail. So in a critical, like memory critical application where you need to optimize for the memory, you need to watch out for this kind of trick that you probably can do on your high level program to compact the memory usage from your program. Okay, so that's the importance of understanding data alignment in memory.